Well, good morning and welcome to Homecoming 2020 at UMass Dartmouth. My name is Pauline Entin and I am the Dean of the College of Arts and Sciences. I wish I could welcome you in person, but I'm glad for everyone that's here with us online or viewing this in video. The world is certainly a different place right now, and depending when you attended UMass Dartmouth as a student, the College of Arts and Sciences has also changed quite a bit. We currently have 18 departments that offer over 40 different academic programs. We're home to more than 3,000 undergraduate and graduate students and over 190 full-time faculty. Some of our newest programs include a bachelor's degree in healthcare services administration through the economics department, a bachelor's degree in health and society, which is our fastest growing program, a bachelor's degree in communication through the English and Communication Department, which is, of course, a new configuration for the English department, new minors in data analytics, and also legal studies. One of the areas I'd like to highlight today is our data science bachelor's and master's degree programs, which are also relatively new. These programs are a partnership between our Department of Mathematics and the Computer Science Department in the College of Engineering. Data science combines mathematics, statistics, and computer science to prepare students to work with large and complex data sets in business, healthcare, sciences, and other fields. The demand for data science professionals is growing quite rapidly. According to the US Bureau of Labor Statistics, there will be an estimated 11.5 million new jobs in data science by 2026. Some of UMass Dartmouth's talented data science faculty are helping the university model and mitigate any COVID outbreaks on campus. Our speaker today, Dr. Scott Field, is another of our talented data science faculty. Scott Field earned a bachelor's degree, well, 2 bachelor's degrees in both mathematics and physics at the University of Rochester, where he chased something called a beauty or bottom quark. He earned a PhD in computational physics at Brown University in 2011. He joined the Department of Mathematics at UMass Dartmouth in 2016. Dr. Field is a Rhode Island native, a lover of burritos, and a hater of the New York Yankees. When he's not simulating black holes, he can be found running out to charge his electric car or watching Netflix. I'm sure you'll agree we're lucky to have him here at UMass Dartmouth, and I hope you enjoy his presentation on discovering black holes and gravitational waves with a look at the recent Nobel Prizes awarded in physics related to black holes. And with that, I'll turn it over to Scott.
Great, thank you for the introduction and for everyone joining us here today. So I'm going to try to give a kind of an overview of some of the recent discoveries and progress in gravitational wave science, kind of taking an historical viewpoint, but really highlighting the recent Nobel Prizes, as well as some work that's being done here at UMass Dartmouth. Okay, so a couple of acronyms that I'll be using throughout the talk. I'm going to try to not use too much jargon, but these will come up again and again. So just to make sure that people are on the same page. GW will be for gravitational wave. LIGO, we'll meet this experiment a little bit later in the talk, stands for Laser Interferometer Gravitational Wave Observatory, and GR stands for General Relativity. This talk also comes about from various online sources that I've sort of shamelessly copied and pasted figures from throughout the talk. So if you want to follow up with any of that to learn a bit more about this topic, feel free to consult these references. So most of the talk will be about explaining this cartoon sort of scenario here. And so the problem kind of begins at the bottom right corner. And you can see here there are 2 objects. Well, now it just became 1. They look like holes that are black. And it turns out that these are 2 black holes. You may wonder why there are 2 or even why there are 1. So we'll get to this a little bit later in the talk. But as a kind of a preview, it turns out that most stars, after they've exhausted all of their fuel, they will sort of collapse back in on themselves and form a single black hole. Now you may wonder how there could possibly be 2. It turns out that our sun is somewhat unique in the fact that there's just one sun in the solar system. and the sun, of course, is a star. Most stars have a partner. They usually form in pairs. And so when this process occurs where the star turns into a black hole, there's already two of them. And so you get something called the binary black hole system. And that's what's being shown here in the bottom right corner. This is also it's a realistic computation. I mean, this took weeks on a supercomputer, and we're just seeing it here as about a 15-second animation. So there's a star field in the back. This is the Milky Way Galaxy, and what we're kind of imagining is if we were looking at the Milky Way, or the galactic plane of the Milky Way, and we took two black holes and put them there, let them orbit around one another, how would we observe the distant star field light? And this is a very realistic depiction of what we would see. Of course, if you see this, this is bad news. It means the black holes are way too close to us. Most of these occur in other galaxies. But this is kind of what it would look like if there were black holes close enough to the Earth that you could sort of see them sort of with a telescope, say. One of the things about black holes is they're very massive. They're moving very quickly, as we'll also see this a little bit later. And these two conditions tell us that they're strong enough, they have enough energy to actually dynamically change the fabric of space-time. And this dynamic changing is what we call gravitational waves. So these black holes, let's imagine they're in some other galaxy, they're orbiting, they're emitting gravitational waves, and these waves eventually reach us here on Earth. So this is kind of a cartoon of what this might look like. Now, of course, gravitational waves are not green, we can't see them. And this is a very exaggerated effect. We would be in big trouble if gravitational waves actually did this to Earth, wiggled it that much. But this general idea that what the waves are doing is slowly stretching and bending matter is the exact effect that it does have, just on a much smaller scale. And then in order to detect these, we have gravitational wave detectors located throughout the Earth, and here are just two of them shown here. So that's the general setup, and that's what we'll be trying to explain today, and how these concepts led to very recent Nobel Prizes. So if your question is, what are black holes and why do we think they exist? That answer is provided by the 2020 Nobel Prize winners. And if your question is, what are gravitational waves and why do they exist? That answer is provided by the 2017 Nobel Prize winners. If your question is, why should I care about black holes and gravitational waves? Well, there are many different reasons. So scientifically, there's a lot that you could learn from them, and we'll talk about that a little bit later. But just as some things that may be of interest, of very wide interest, for example, if you wanted to know where gold comes from, turns out that the answer is gravitational waves have told us that. And if you're worried that there could be black holes nearby, it turns out that there may actually be another planet in our solar system that may be a black hole. That's something that's currently being looked into. So these black holes are everywhere, and they can tell us a lot about things in the universe, even things that you wouldn't expect. So for example, where gold comes from. So this problem is hard. It has a 100-year history. So the story begins in 1915 with Albert Einstein, where he sort of wrote down the equations of general relativity. And then much of today will just kind of be quickly glossing over these landmarks here. So there's not enough time to really fill in the full story. So I'll just try to give some highlights. Throughout the 1950s and 60s, Yvonne Schoch-Bruhat was very instrumental to showing that you can even solve the Einstein equations, the equation of general relativity. And a little bit after that, once these solutions were shown, people started wondering very seriously about black holes. So the very fact that we believe black holes exist, this was developed between the 60s and the 90s and resulted in the 2020 Nobel Prize. We'll meet these three people again a little bit later in the talk. And one of the things that we do here at UMass Dartmouth is simulate black holes on computers. That wasn't possible until 2005. And in 2015, well, gravitational waves were observed by LIGO. So this is one of the gravitational wave detectors here, and that resulted in the 2017 Nobel Prize. So we're going to kind of give an overview of what is gravity, because that's very important for understanding these next two questions. Then what are black holes and what are gravitational waves? So gravity, as you may have encountered in high school physics or maybe some introductory physics classes on mechanics, you may be presented with this sort of framework here. So the story kind of goes back to Isaac Newton in 1687. He wondered why apples were falling in his backyard. Actually, it was during a pandemic when he discovered this. I think when you're quarantined to your house, you have a lot of free time to think. And this was one of his most productive couple of years in science, is when he was under quarantine. So he wrote down the theory of gravity, and that was basically what we believed to be true for about 300 years, or 250 years. And the general picture kind of looks like this. So this is a diagram of what you may think of as gravity, according to Newton. Gravity is the effect of two massive objects pulling on each other. So for example, if you were to let an apple fall or something, the earth is pulling down the apple. And strictly speaking, the apple's pulling up the earth, but we don't really, the earth is so big it doesn't move that much. And we can predict what the forces are according to Newton's equation here. Suffice it to say, this theory has no black holes, it has no gravitational waves, and this required a reinterpretation of what gravity is. This was the picture for many hundreds of years. Einstein came along in 1915, and he was puzzled by basically this figure here. So how is it possible that these two bodies, maybe it's two planets, could instantaneously feel the effect of one another? So this was kind of something he didn't like. He didn't think there should be instantaneous kind of effects. And this deep thought, which took about 10, 15 years for him to develop, led him to this picture that's up here on the top right. The basic idea of general relativity is that mass doesn't exert forces on other objects, but it curves the space and time around them. But understand that, we could imagine if we're far away from these this is the moon and the earth here, we're far away from those up in this grid. That's a regular Cartesian grid. So for example, if you were in New York City walking down streets, this is kind of a gridded structure. And if you were to, let's say, draw a triangle in New York City or anywhere else, you would measure the angles and you would find out they're 180 degrees. So that's a geometric kind of concept. When we get close to the Earth, which is massive enough to warp the space around it, the picture looks a little bit different. You can see here that the grid lines are being distorted. And for example, if you were to draw a triangle in the vicinity of Earth, the triangle would not have angles that added up to 180 degrees. So that's a consequence of the curved space due to the effect of the Earth's mass. It has all sorts of different effects and manifestations, which we'll come to later. But this is the basic picture here, where you should think of gravity as now being a curvature of space as opposed to an instantaneous pulling of two bodies on one another. So as an example, what does this kind of look like? So imagine you're in an academic quad and it's a nice day and you're looking at a clock tower and roaming around on the grass here. So this was pre-quarantine. You can see all the people outside talking to one another. And a black hole appears on the quad. What would happen? Again, this is not a cartoon. This is a realistic simulation that was done to show the effects. So if you see this, you should certainly get out of there. This is not good news if you see a black hole in the quad, but you can now see what the effects would look like if you were to see one. So here's the original picture, no black hole. And here's the picture now with a black hole. So we just said, what does very massive objects like black holes do? It curves the space. And the space that's being curved is the space that light has to travel to get from the clock tower, because the ambient light of the atmosphere is reflecting off of the clock tower to your eyes. So if there is no black hole, the light travels in a straight line as if there was like a laser beam pointing from the clock tower to you. Now it's traveling in a curved space. So you can see here the effect of this is the clock tower appears to be bent, mostly because the clock tower light now has to kind of go in this curved line, which gives the optical illusion that the clock tower has been kind of pushed out and curved. And if you notice, there's even weirder things. So if you have a kind of a keen eye, you'll notice an inverted clock tower down here. This is light that would have reached your friend to your left. And instead of reaching them, it now kind of gets pulled around the black hole and comes back up to your eyes, where you see an inverted clock tower. And if you were to zoom in over here, which we really can't see in the figure, there's yet another clock tower. And in fact, there's infinitely many clock towers due to the light getting trapped around the event horizon of the black hole. And sometimes this is interpreted as people saying that the black hole, the entire history of the universe isn't somehow coded near the black hole's event horizon, because all of the light that goes by it gets trapped there and then eventually gets flung back out. Not that we can use this to really see back into the infinite past, but in principle, all of that information is actually contained there. But we can already see this kind of at work here by this inverted clock tower. So these are equations that we have to solve. So I mean, equations were solved to get this picture here. So this is not some sort of experimental thing that we're doing or phenomenological thing. These come from well-defined equations, so we're not really going to talk too much about the equations other than to say that you can write them down, and here they are. And the way to view this is the stuff on the left-hand side. This is what you're solving for, which is the geometry of the space-time, the curvature. And everything on the right, this is where the matter is. Where is the black hole? Where's the stars and the planets? So if you know where the stars and the planets are, and wherever the black holes are, that tells you how to populate the right-hand side, this weird symbol T mu nu. And if you have that, then you can figure out what the curvature of space-time is. And then you can go about making predictions of what you would see, kind of like this figure here. So this is a very complex, even though it's just written down in a very compact way, if we were to expand and ask what all of these terms are, things would quickly become unwieldy. So that's why we don't really do that here. But I'll just point out that these equations give well-defined predictions if you can solve them for a variety of things. So we already saw lensing on the academic quad. That's one prediction that you can get if you solve these equations. If a gravitational wave passes by, and there are always gravitational waves coming through the Earth, the distance between UMass Dartmouth and Fenway Park changes because the gravitational wave will compress and stretch the space between these 2 points on the map. It's an effect we don't notice because it's small, but it's always happening. And there's also something called time dilation, which maybe was popularized in this recent movie Interstellar, when people go down to this planet and they come back up to and the planet's near a black hole. They come back up to the spaceship. They're young, and the person on the spaceship has aged by like 30 years or something. So this is another effect of consequence of solving these equations. And as it specialized to Earth, for example, if you want to live a little bit longer, you may want to move to Boston. Strictly speaking, you're going to age a little bit slower in Boston than Denver, because Denver is at a higher point in the gravitational field. This effect is very small, so maybe you're only going to be saving a couple of milliseconds over the course of your life, but cumulatively it can add up to quite a lot. So for example, the Earth has been around for about 4 billion years, and the core of the Earth is at a lower gravitational wave or gravitational point than the surface, so it's aging more slowly. And I think if you work out what the numbers are by kind of solving this equation specialized to that, you'll find out that the core of the Earth is about 2.5 years younger than the surface of the Earth. So these effects can accumulate in certain cases, even on the Earth. You don't need anything like black holes to get it. So if we were to unpack the equations, you would get this. This is just to show you that we're going to use computers to solve these equations. The most simplest specialized case, if you were to unpack the Einstein equation here, you get this entire mess. And if you've seen a calculus class, or you remember some calculus notation, these are derivatives here, and there are all sorts of terms. And this is a very messy coupled partial differential equation. And so that's kind of the equations we have to solve, though, if we want to make these sorts of predictions. So the big picture questions here are, do solutions exist? So, I mean, the equations are very messy, so can we even solve them? If we can solve them, what evidence do we have to believe that they would predict black holes? And if we can solve them, what evidence do we have to believe that they would predict gravitational waves? So none of these questions are obvious. In fact, as we'll see, many people debated vigorously that these things did not exist, and it took about 100 years to sort the whole thing out. So you have to have a lot of patience to get to the end point here. So the first question is just simply, can we solve these equations? The equations are messy, so it's not really clear. And this matters quite a bit, because there's no point in asking, do black holes exist or gravitational waves? And you certainly can't win any Nobel Prizes if the equations don't have solutions. You can't make predictions unless you can solve them. So to kind of get a flavor of what this even means, we'll start with a simpler case where we can kind of get a sense for when things can break down. So for example, if you were in an algebra class and you were given this question on a test, and someone said, for what value of x is this equation true? So what you would do is start manipulating some of the terms. So you would do 12 minus 8 and you would get 4. You do 7x minus 5x and get 2x, and then you'd notice the 2x's cancel, and so you would get 4 equals 5. So if someone asks what value of x can you solve this equation, the answer is there are no such values. You cannot find an x that satisfies this equation. So not all equations can be solved. So to understand how to apply this concept to the Einstein equations required a lot of mathematical machinery that actually wasn't even around in 1915 when Einstein wrote down his equations. Most of this was developed in the 30s by a group of mathematicians working at largely at NYU. So actually this was right around the time that World War II was starting. So a lot of European scientists and mathematicians came to United States, and they started an applied math center at NYU. And actually here they are having a picnic in White Plains, New York. So they developed these tools for trying to understand when you can solve differential equations like the Einstein equation. But they were looking at, I guess, comparatively simple cases. And so the real breakthrough came in 1947 when a grad student at the time, Yvonne Schoch-Bruhart, who was in France, so this was actually a little bit after World War II, started to write or wonder, can we apply these techniques to kind of come up with ideas about, can we solve the Einstein equation? So that was her graduate thesis project, a quite ambitious one, in my opinion. I certainly would have been kind of upset if my advisor told me I should be working on this. But somewhat miraculously, she did this within a 5-year period. So 47 is when she started. In 1952, she wrote a sort of historically important paper showing that you can solve the Einstein equations under somewhat general conditions. And then the final theory, which her and Robert Garrosh, who was at University of Chicago, worked on in 1969, sort of showed in just very general cases you can solve the Einstein equation. So that's good. So we know that solutions exist thanks to her work, and we can start asking about interesting solutions that are being predicted. So for example, black holes. That's one prediction of the Einstein equation if you solve those equations. And they're very weird. We already saw they did weird things with the clock tower. So if someone tells you that black holes exist, you should be looking for an extraordinary amount of evidence, because it's somewhat an extraordinary claim, because they're very bizarre. So this actually leads to this Nobel Prize in 2020. So I'll say right off the bat, so 1 year after Einstein proposed the general theory of relativity, Carl Schwarzschild immediately recognized that you could have solutions like black holes. But this was more of a mathematical, in some sense, people thought, trick. They thought that these would be impossible to actually form in practice because they were just too weird. But at least as early as 1916, people kind of had this in the back of their minds that the Einstein equations could produce a black hole type solution, although they weren't really called that at the time. The basic idea for this is if you have mass like the sun, say, there's no black holes, but it's a very heavy, massive object. If you were to shrink all of that mass down into a very, very small region of space, I think for the sun, we'd be talking about something on the order of a kilometer. So if you took all of the mass of the sun and could somehow squeeze it into a radius of a kilometer, this effect of space and time sort of stretching and bending, in some sense it breaks. So that's given by this cartoon over here. When a black hole is formed, if you're able to push the matter down into very small regions, a couple of new features show up. So one feature is this event horizon. So this is literally the region that separates events. So if you're inside the black hole, you cannot communicate with the outside. You cannot do it through radio waves. You cannot do it through sound waves or talking or waving or anything like this. There's no way for you to communicate with the outside world. So it's literally a horizon or a barrier of events. And this is due to the very severe warping of space-time. So that's actually, if you're at this point to the event horizon, you're kind of in tough shape. This is not good to be there. But there's actually an even worse place to be, and that's the singularity. Whoops. The singularity is where space and time literally are not defined. So it doesn't make sense to even go there, but you can get closer and closer to it. So there's no concept of time at the singularity. There's really no concept of space there. And as you get closer and closer to it, here's an astronomer getting closer, or an astronaut getting closer to the singularity, you sort of start stretching out. And that's due to this kind of the severe stretching of space and time, sometimes called spaghettification. So you would keep stretching out and eventually you would get torn apart. So it's not a very pleasant experience. So it's much better to be at the event horizon than the singularity, but neither of these are very good spots to be at. So very weird, bizarre things happen, and that's why black holes were dismissed as completely implausible solutions. So at this point, it's also good to kind of get a sense of what we even mean by implausible solutions. So a more familiar example might be if you're looking for apartments or houses and someone gives you a floor plan. they may tell you that the bedroom is 49 square feet. Okay, so here's the bedroom here, and we already know kind of ahead of time if it's a square bedroom, it's probably the walls are going to be 7 by 7. But if you're looking at this from a purely mathematical point of view, the equation you would write down is if you let x be the wall's length, x squared equals 49. That's the statement that the square footage in the bedroom is 49 square feet. And so if you were to just write down this equation and blindly look for solutions, you would find that the walls could be 7 feet or they could be minus 7 feet. So in this case, we immediately recognize that minus 7 feet is not plausible, so it's excluded. And we would say, okay, the walls must be 7 feet. So it is true that if you have an equation, you may find sometimes they're called spurious or unphysical solutions. And maybe the black hole is one such spurious solution. That's what people thought for many decades. And the real breakthrough came in the 1960s with Roger Penrose, and this work led to the 2020 Nobel Prize. He showed in somewhat generalities that black holes are robust predictions of general relativity, which is to say these are not contrived special mathematical solutions, but they will generically occur when stars collapse. And so here's a diagram here kind of showing this. So just for some sense of what scale here. So our sun is a small star. And so eventually it will follow this path here. So this is not pleasant either, so this is something that would be in the distant future of Earth, but it's not going to form a black hole, it'll form a white dwarf. If the star is very large, however, it follows this other path. And eventually one of two things can happen. If the star is sufficiently large, it can form a black hole. And if it's sufficiently large, but not so large that it forms a black hole, it could form into a neutron star. And so Roger Penrose was the first person to sort of describe and give convincing mathematical evidence that this secondary path were possible, and you can actually get black holes through astrophysical kinds of realistic scenarios. Here's a picture of Sir Roger Penrose. He was knighted many decades ago, meeting with Katie Rink. She's a very recent master's student here at UMass Dartmouth. So she did her undergrad at University of British Columbia, and Roger Penrose gave a talk there. And here they are chatting about some science. So this is basically the theoretical picture of black holes, why we should believe they exist from a theoretical point of view. Of course, experimentalists immediately want to go out and test the theory because they may not believe Roger Penrose. They actually want to see black holes for themselves. And this led to the second half of the 2020 Nobel Prize, which was shared by Andrea Ghez and Reinhard Genzel. And what they did is they basically asked, well, what's at the center of our own Milky Way galaxy? And what they found is that there is a giant supermassive black hole there, about 4 million times the mass of our star. So a little bit more about how this worked. So Andrea Ghez, she's an astronomer. She works with telescopes. And whoops. Oh, I guess a slide got cut here. Anyway, there was supposed to be a picture of the the observatory, which is the Keck Observatory in Hawaii, but somehow this other picture got there. And she's one of the directors of the observatory. And what she did with her team is to observe the motion of stars around you didn't know it was a black hole to start. The motion of stars near this very large, massive, compact object at the center of the Milky Way over many, many, many years. In fact, it took about 25 years to really trace out the orbit of these stars. Just like planets evolve around our sun, stars can kind of orbit around the supermassive black hole. And sort of by tracking the motion of the stars over time, you can build up an understanding of the trajectory of the star. And then you can use just Keplerian dynamics of the motion of astronomical objects to figure out and deduce what the mass of this central body must be. In this case, it's 400 million solar masses. And there's no stars that we know of that can be that big. So this is one piece of evidence for there must be something very strange and exotic there, which we now know to believe to be a black hole, a supermassive black hole. So here's one such star. This is sometimes called the S2. This is a kind of one of the special stars that orbiting the supermassive black hole. But there are many, many more. And this picture down here shows some of the trajectories of the stars orbiting the central black hole here. So you can see them in different colors. You can see down here, this picture was compiled between 1995 and 2014. So again, this takes a lot of patience. You just have to every year kind of ask where the stars are. But it's of course a lot more than just that, because there's a lot of things in between the stars and the telescope. So some of the breakthroughs that she made was in something called adaptive, I think it's called adaptive radio or optical astronomy, where you sort of try to correct for the light that's coming out of this system in a way that you can really get good angular resolution of these stars here. It's a very challenging problem in experimental physics. So now that we know that black holes exist, we can move on to the next question. What about gravitational waves? And why this matters, do gravitational waves exist? Well, we had to convince Congress to build gravitational wave detectors. And these detectors cost billions of dollars, and Congress is not going to fund billion-dollar projects unless we know that they're gonna find something. And this wasn't very clear either. So also in 1916, Einstein recognized that gravitational waves could be a solution to his equation, but he also dismissed them as being unphysical, just like black holes were dismissed as being unphysical. So I guess the common theme here is we should be trusting the math a little bit more than our intuition, because these solutions all turned out to be very important and very physical. So just a couple of landmarks to sort of the discovery of gravitational waves. So on the theoretical side, as late as the 1930s and even 1940s, this was very hotly debated topics. So Einstein with this other collaborator, Rosen, who also were the people who discovered or proposed wormholes, but they wrote this paper on the non-existence of gravitational waves. So the paper kind of claims that they arrive at the interesting result that gravitational waves do not exist. That was in 1934. And actually there was a lot of debate in the community, and really the moment where things sort of changed was this very historically important conference in 1957, the Chapel Hill Conference, when there was a sort of a discussion and somewhat of a proof was given that gravitational waves were indeed real, because it was shown that they could dissipate heat. And if heat is real, so if gravitational waves are producing heat, then they themselves must be real. These are some of the people that kind of led that effort. So after gravitational waves were predicted to be real, people went out and wanted to find them. And the technology really wasn't ready until the 1990s. And this is when LIGO started to get constructed, the late 1990s, early 2000s. And you can see here, there are a couple of gravitational wave detectors scattered throughout the Earth. And here's the two main ones in the United States that's funded by the National Science Foundation. So these are just giant arms. There's a laser beam bouncing back and forth. There's a mirror way at the end here. There's another mirror here. And these arms are 4 kilometers long. And this is what happens when a gravitational wave passes by. So this is our animation from before. And here's this triangle is one of the gravitational wave detectors. So if you imagine the gravitational wave coming in, let's say, and we're looking at the detector from a bird's eye overhead view, you can see here in this bottom right corner that, I guess, yeah, there it is there, the bar just moved. The arm lengths between the two sides change as a function of time. And that's because the gravitational wave is stretching and squeezing the space in between the two mirrors. There's a mirror at the far end here, and then there's a mirror down here. And so these detectors are able to measure very small changes in the path length due to the gravitational waves passing through the Earth. So that's roughly how the detector works. And the very, very first gravitational wave detection happened in 2015. So September 14th, 2015, a gravitational wave passed through the Earth, and the detectors recorded this signal. So you can see over here, there's really no signal. This is just the noise of the detector. And actually, you can see on the y-axis, this is strain. So this is roughly the relative change in the path length of these two mirrors. And the x-axis is time. So we're recording things as a time series, just like maybe a microphone, say. Instead of sound waves, we're recording gravity waves. And at some point, you can kind of see there's a structure to this pattern, and it turned out that through some careful data analysis that this pattern here is the gravitational wave. It's the effect, the observation of a gravitational wave. This is a very, very, I mean, this is almost remarkable that this can even be done. And I had nothing to do with this. These are all the experimentalists. These mirrors are 4 kilometers apart, and the gravitational wave, it's changing the mirrors by distances smaller than the size of a proton. So you have to be able to very accurately measure very small changes in these mirrors over very large distances. So these detectors are extremely sensitive. It took decades to kind of get that technology up and running. So actually running a little short on time, so I'm going to skip a couple of slides. But I will say that this really was the first time that gravitational waves were kind of widely put on the map, kind of in the public conscious. So here's a New York Times article proudly stating that scientists have proved Einstein correct by finding gravitational waves. Usually these science stories are buried at the end of the paper. Here it's featured prominently at the beginning. Also, just kind of by luck would have it, Interstellar was being released around this time. And here's Kip Thorne, who's one of the founders of LIGO, doing some math with Jessica Chastain, who is one of the lead actresses in the movie. And over here, you can see this is a subway in New York City. And if you read what the advertisers say here, it said if scientists found gravitational waves in outer space, if it were only that easy to find an apartment in New York City with a walk-in closet. So the advertisers thought that enough people knew about gravitational waves that we can actually start using them in our advertisements on the New York City subway. So this was sort of a big historic moment for the field. And in 2017, the Nobel Prize was awarded to the 3 people who founded LIGO. Before 2017, Kip actually visited UMass Dartmouth. So here's Kip Thorne here. Here he is over here. And this is a Physics of Interstellar event. And here are some UMass Dartmouth faculty and 2 of the directors of the Scientific Center for Scientific Computing and Visualization Research, Sigal Gottlieb and Gaurav Khanna, and some of our PhD students. They're out having lunch somewhere with Kip. And gravitational waves, they're kind of the first part of the story. So once you are measuring these waves, you can do all sorts of interesting things with them. So for example, you can ask, is Einstein's theory correct? So you can test the predictions of the theory. How is gold formed? So I'm happy to answer that more in detail at the end if people are interested. That is something that we've learned through gravitational wave signals. Very exotic things like how many space dimensions do we live in? We think it's 3, but if it were more than 3, gravitational waves would encode that information as well. Some of work was done with, she's now graduated, but at the time she was a mathematics undergrad here. She's now doing her PhD at RPI. We actually worked on improving the model of gravitational wave propagation because they travel over very long distances, many hundreds of millions of light years. And so if you can more accurately model the way that the waves propagate, you can extract more information from your detections. Okay, so that sort of concludes one part here, which is basically we now know that we can solve Einstein's equations and that black holes exist and that gravitational waves exist. Through the work of these researchers. So now we can see what these waves look like. This sort of has an interesting story, and this ties into what we do here at UMass Dartmouth. We try to solve these equations, which are very hard to do, almost impossible to do with a paper and pencil, by putting them on a computer through the design of sort of advanced algorithms. Okay, so what is this field all about? So the idea is to use kind of mathematical tools, algorithms, but also very large computational resources to have the computer solve general relativity on our behalf because the equations are too difficult. This is the general setup. So what we would like is to tell the computer what remember the very first picture, we have 2 black holes orbiting one another. These black holes have mass. It turns out they're kind of like spinning tops, so they have spin. And we would like to tell the computer, given the masses and the spins of these 2 black holes, what, for example, would be the gravitational waves coming out of this system. So that's what we would, for example, like to ask the computer to do on our behalf. It turned out that actually this story goes back to 1964. So the very first attempt was by Susan Hahn. She actually made a lot of fundamental contributions in applied mathematics. And then she worked on building one of the first supercomputers at IBM in New York. And she had exclusive access to this machine, which is pictured here in this giant room here. And she collaborated with Richard Lindquist on this idea of, can we have the computer solve black hole collisions? So if you have 2 black holes and you throw them at each other, what would the gravitational waves look like? That's the kind of question that they were hoping to answer. So this was an historic point in this field, the very first attempt to do that. The problem is that there are many things that weren't really quite right at the time. Even though this computer is large, it takes up a whole room and costs $3 million. By modern standards, this is a very weak computer. It only computes 1 megaflop. For point of comparison, my phone, which is not even that new, it's a Galaxy S6, computes about 700 megaflops. So it's 700 times more powerful than this $3 million machine that took up the whole room. And also, for reasons I'll explain in a second, the program didn't even finish. It just crashed. So it wasn't just that the computer wasn't big enough, there was something more fundamental wrong. So remember, Yvonne Jacques-Bruhat, she told us that solutions exist. But a very different question is, what is the right way to get the computer to solve these equations? There are many wrong ways, and for anyone who's familiar with computers, sometimes the computer just locks up and crashes. So this is the blue screen of death. And that's, roughly speaking, what was happening to people trying to solve black holes on the computer. The computer just kept crashing, and people didn't quite know why. In fact, it was a big problem because from 1964, which is when Susan Hahn first tried to solve these equations, to 2004, no one could get black holes to simulate on a computer. And it was becoming a big problem because LIGO was funded by Congress in 1993, and we didn't even know what gravitational waves looked like because we had no way to solve the equations. Here, the big breakthrough came in 2005 with Franz Pretorius, who was somewhat working by himself. He was sort of a postdoc at the time, and he had some big breakthroughs building on work of previous people. So he was the first person to simulate 2 black holes. And today, about 15 years later, many research groups have their own code to do this. So we can get an example of what this looks like here. So I've muted Brian Green so we can just kind of see what's going on. So before those black holes were there, that was flat space. So there was no matter. And now if we throw down 2 black holes and just imagine that they're orbiting one another, this is roughly speaking what the waves would look like. So it's very similar to what would happen if you were to stir water waves, say, except now we're stirring space and time, and these waves propagate over long distances and eventually reach Earth, where they're finally being detected. Again, the effect is greatly exaggerated. But that now we know what these waves look like thanks to these computational breakthroughs. So I'm running a little short on time, but I do want to just kind of briefly mention some ongoing work at UMass Dartmouth and future directions. The things that we're most interested in and working hard on is to build computational models and codes in order to process data. So in order to extract any science from gravitational wave observations, we need to know what the signal looks like. And the better job that we do at modeling the signal, the more accuracy we can extract from the detections. So a lot of this work is being done through the Center for Scientific Computing and Visualization Research, which is a multi-interdisciplinary center drawing from math, computer science, data science, and physics. And there's a variety of research groups that are all kind of working on these topics. We've had many grad students. Some of these have graduated and gone on to other positions and postdocs in the field. Some students are currently still here working on these topics. So it's a very large, kind of vibrant group working on different aspects of this problem. Roughly speaking, there are 3 research groups that are contributing to these efforts. So one is the numerical partial differential equation group. Einstein's equation is a partial differential equation, and so putting it on a computer that's the numerical part. And so people working in this group design the algorithms and the computing codes in order to simulate these problems. In fact, Sigal Gottlieb, who's one of the directors of the Scientific Computing Center and is a faculty in the math department, she was recently awarded a very prestigious prize in 2019. They only give a few out of these each year to applied mathematicians for some of her fundamental work in applied kind of computational research, which actually had a very big impact on solving binary neutron stars in a computer. In fact, I would argue that you couldn't do it without some of the techniques she developed in the early 2000s, mid 2000s, and still is working on today. There's also a gravitational research group, which really focuses on applying these numerical techniques to the problem of gravity. And again, they're multidisciplinary. Dana Fine and myself are in the math department. Gaurav, Professor Xu and Rob Fisher, Bob Fisher, they're in the physics department. And Richard Price, he's actually at MIT, but he has a joint affiliation at UMass Dartmouth. And then data science, which I'll kind of conclude with in a second. This is a large group spanning math, physics departments, and computer science. And I will kind of briefly focus on what's kind of ongoing work in that regard for the gravitational wave problem. So briefly, this is a problem of machine learning. So data science is broad. It means a lot of different things to many different people. I'm mostly going to be talking about machine learning. So this picture is somewhat pessimistic or optimistic, depending on your point of view. The point here is that machines have been slowly beating us a lot of things that we thought only people could do. So for a long time ago, we conceded on chess. Computers have been able to beat people for a long time with chess. But said, oh, we're not going to ever lose in Go. Go is too complicated. It requires a lot of creative thought. But very recently, Google designed a machine or an algorithm that can beat the world's best Go player. So here he is losing in Go. This is not good. They've also beat us in, computers have beat us in Jeopardy. So here's Watson, the IBM computer, which actually probably Watson, a lot of this work goes back to Susan Hahn, who was working at IBM. And actually it was the same facility in New York that both produced that supercomputer and also Watson. Here's Watson beating Ken Jennings and Brad, I'm not sure his last name, but beating him in Jeopardy. They're slowly encroaching on other fields. So self-driving cars is something that eventually computers will probably be doing. And in medicine, health analytics, this is a very hot, fast-moving field. So for example, radiologists would typically look at images and try to diagnose the likelihood of cancer or something else. But now a lot of this stuff is being done by machines. And it's probably only a matter of time before the machine is also better. So this has become to a point where even presidential candidates have started talking about these issues. So if you remember Andrew Yang, he was a Democratic primary candidate, and his main platform was addressing the issue of what happens when computers take over many jobs that people have typically done. So there aren't many professional Go players, but there are a lot of truck drivers and cab drivers. So he was trying to figure out what we should be doing as a society when machine learning starts encroaching on other areas of life. So that's certainly a topic for another day, but I'll just point out that this is what we're using in the context of gravitational wave classification. So classification is one of the things that machines are best at. So for example, if someone sends you an email, an algorithm will try to understand, is it spam or not spam? So that's a classification problem with machine learning. If you do mobile deposit of a check, someone has to figure out what you've written on the check, what the numbers are. So handwriting analysis, that's another type of classification problem with machine learning. Turns out machine learning is really, really good at classifying things. Here are two examples. And I'll just point out that actually machine learning, even though it's new to many people, it was actually discovered in the 70s. And the reason why it wasn't used is it requires a lot of computing power to actually leverage the algorithms that were developed then. So it was somehow the algorithms were way ahead of their time, and now the computing power has sort of caught up with it. So here's another example that's somewhat relevant to what we're going to be doing in a second. So imagine you have a bunch of pictures. So maybe you upload pictures to YouTube or Instagram, and these companies need to tag and categorize the picture. So maybe the camera's not even that good, so you have a very blurry picture here, and you send this through this is kind of a graphical way of representing a machine learning classifier. I'm happy to talk more about that if there are any questions. But at the end of the day, at the output, it assigns some probability. So what's the probability that your image is a dog versus a cat? And that's roughly how these machine learning algorithms work. They assign a probability of being in one class or another class. This is called image classification. So we're looking at applying these ideas to gravitational wave classification. And this work was really led by Dwyer Deegan, who's a data science undergrad, although he's recently was admitted to the accelerated 4+1 program. So he's actually wrapping up his master's degree. But most of this work was carried out with him as he was an undergrad, and he really did all of the coding and all of the heavy lifting on this project. The basic idea that we're trying to ask is there a gravitational wave in the data set? And so here are two data sets. It's really not important what these labels are. But if I told you one of them contains a gravitational wave signal and another one does not, the human eye, at least my eye, is not good enough to see which one contains a gravitational wave signal. They look very similar to me. But if we were to kind of, so this is mock data, so it was prepared, so we know which one has the signal. It turns out that this one does not, so we label it as 0, and the bottom one does. So this is the one that has the gravitational wave in it. And so Dwyer's project was largely to design numerical or machine learning algorithms to solve this classification problem. So I'll just point out that this, to me, is a very interesting area because it has an opportunity to really get a lot more out of the gravitational wave science. So I'll just kind of mention that this is a very old idea. Like you need to, not machine learning part, but classifying things. And typically it works by pattern matching. So one analogy might be if you're in a very noisy car and the radio is very weak, you can't hear it, but something's coming out of the radio. You could use pattern matching to try to understand what the song is. In order to do this, you would have to have a catalog of all possible songs coming out of the radio. So if it's tuned to a rock station, you would find all of rock songs that were ever recorded. And you would do this data analysis technique called pattern matching. So this is very slow because you have to march through the catalog of all possible songs. Machine learning classifiers promise to be much faster. They don't need a template of possible songs to do this pattern matching. And because it's much faster, you can potentially do something very interesting called multi-messenger astronomy. So if you were to detect the gravitational wave quickly enough, you could tell other telescopes that maybe look in different bands, maybe they're looking at gamma rays, radio waves, or other optical bands, you should go look at this point in the sky because something is interesting coming from there. There's some gravitational waves. So this is sometimes called low latency multi-messenger astronomy. And at least to my mind, these machine learning classifier techniques are really one of the keys that will sort of enable this to kind of fulfill its full promise. And I'm also personally excited about it because we just submitted this paper to a journal. You can see here, October 9th, 2020 is when it was uploaded to the archive, which is a preprint server, so you can go and look at it if you want. And we just submitted it to the journal. This also happened to be the first paper I had written with an undergraduate student. And I think it turned out to be really nice, all thanks to Dwyer. He did all of the hard work here. But I'm happy to talk a little bit more about this if people are interested. Okay, so I'm way over time, but it's not quite 11 yet. So I'll just kind of leave up some final thoughts here. Gravitational wave science, hopefully I've convinced you there's a very rich history here that is highly interdisciplinary with math, applied math, computational science, data science, machine learning. And really these Nobel Prizes are just the beginning. So there have been 2 handed out, but there are many, many more in the works to my mind. One very important discovery in 2019 was by the Event Horizon Telescope, where this collaboration was able to image a black hole. So here is the black hole here, which is the center of another galaxy called M87. And so you can see it here. And this is the first time we've actually seen a black hole. And actually there's a somewhat famous picture now of the person who first saw it. So this is Katie Bowman. She was a postdoc at the time at MIT, and she wrote a lot of the algorithms that were able to decode these images, sort of denoise it. And you can, if you can kind of see here with your eye, whoops, there's basically this picture that I'm showing here is popping up on her laptop. So that was in 2019, and actually now she's a professor at Caltech, kind of continuing with the computer vision, computer science type problems. So this is possibly a Nobel Prize in the works. And also for gravitational waves, there are new detectors coming online. The European Space Agency is going to launch one into outer space that will look for a whole new class of signals that I'm happy to talk more about. And then at UMass Dartmouth, we're mostly focusing our efforts on developing the algorithms and models and machine learning tools that will hopefully extract more science. I apologize, I'm way over time, but thank you for listening. Hopefully I didn't bore anyone.
That was fabulous, Scott.
Questions.
That was great. Thank you so much. And like I said before we started, this was a great presentation. I'll make sure that we get this out to our alumni base and donors and things like that, because there's a lot we can use here. And I'm sure admissions can use a lot, especially for getting prospective students as well. So thank you. That was very well done.
Sure, thanks, no problem.
Fantastic, fantastic.
Well,
It really was, Scott. Thank you.
Oh, thanks.
Yeah,
Thanks.
I really enjoyed that too, Scott. And you did such a great job, Scott, of making this really accessible that actually I'd also, Josh, I don't know how the recording works, but another group that I would like to have access, if Scott agrees, are the folks in STEM ed. You know, and Scott, you probably know Walter Strube, Sheknoza, Stephen Witzig, and others. because you did such a good job, Scott, of making this accessible, that I think even students in maybe like a high school honors physics class or something could identify with elements of it. Again, it's sort of, I think you also did a job of emphasizing, that people start early working on these problems. They start as undergraduates and so forth.
Yeah.
I think it's
a lot of undergrads and grad students. Yeah.
Yeah. So I think that's great. And I know, we're over time and so forth. And I know Josh and
yeah, sorry about that.
but I actually am genuinely curious. I do not understand the relationship between this and the formation of a heavy element like gold.
Okay, yeah. So actually, I'm happy to talk about that. So the reason why gravitational waves were important in this discovery is that previously no one knew how gold or platinum or any heavy element was formed. Just completely a mystery. There's no mechanism on Earth that would form such things. It was suspected that stars, when they explode, because this is a high energy event, would fuse these elements together to get these certain kinds of materials. So in 2017, a different kind of gravitational wave was produced by two merging binary neutron stars. And these binary neutron stars are very compact and exotic, like black holes, but they're made up of matter, basically an exotic form of matter just called, basically they're like a neutron soup. But when they collided, they emitted gravitational waves, and that allowed people to go look. So this was not low latency astronomy, but after the gravitational wave was detected, people were able to say, okay, we kind of know where in the sky this thing is, and let's point our telescopes there. And through spectroscopy, they were able to see that the light at certain line elements were associated with what gold and platinum and these other heavy elements would look like. Because I think when I'm trying to remember my quantum chemistry here, actually probably just even regular chemistry, when the electrons jump energy levels, the different atoms or elements will emit different kinds of light. And so if there's a bunch of gold being produced in that part of the sky, they're all emitting light of a very certain type of characteristic. And so the telescope saw that light, and because the gravitational wave was detected, we also knew that there were two binary neutron stars that had collided. So those two pieces of information together was what led people to conclude that now we actually know a mechanism for producing gold and platinum. So it wasn't just the gravitational themselves, it was the two things together. Yeah.
Right. So if I'm understanding correctly, what you're saying though is that that part that's actually matter, when the two things collide, some of it essentially gets sent out as almost like stellar dust.
It's called, yeah, it actually is called ejecta. Exactly. It just kind of, after the collision, a lot of it just flies off and as a big cloud. And so it's moving very quickly, but it's so far away, it actually doesn't look like it's moving at all to our eye, or at least the telescope.
Mm-hmm.
But it's emitting a lot of light. So because everything is such a hot, energetic event, that these elements were in highly excited states. And so it's radiating away light by the energy levels dropping. And it's that characteristic that we see. But you're right. It's just like actually, if we waited long enough, stellar dust is almost certainly the result of these explosions. After a long enough time, it sort of diffuses around.
So it's probably not strictly inaccurate to say that gold rains down on us.
Yeah.
But that's not where the gold from the Earth comes from. It comes from the fact that there was this, like, prior to the formation of Earth, there were these particles that became part of the coalescence. Planetary evolution is not something I work on, but my understanding is that, I mean, the Earth is about 4.5 billion years old. Before that, the Milky Way was very active at producing stars and dying stars. And so there was a lot of this stellar dust floating around, and eventually it collapsed and coalesced into planets. Yeah. And so the planet is largely made up of remnants of stars. Yeah. Yeah. So the gold, one could say the gold on Earth is older than the Earth. Oh, definitely is. Yes. Okay. Yeah. And you're right. It's still raining down. So, I mean, we certainly don't see it because it's such minute traces. Yeah. It's definitely true. I'm not going to go pan for it. No. We shouldn't do like stellar mining of gold dust. But it's certainly true that like it must be falling down. It's just very dilute. Yeah. along with every other, like, is this also true of, say, like, I don't know, uranium or something else that's super big?
My understanding is, yeah, anything that has anything that's above iron in the periodic table pretty
Which
much
is a lot.
which is a lot, must come
Yeah.
from this kind of merging of two binary neutron stars or stars going supernova
Right, because we can't generate the kind of energy necessary to do that.
to fuse them. That's right. Yeah.
So that's really interesting.
Yeah.
I never would have, like, that's just so, I don't know, it just seems so out there, right? You know?
Yeah. Yeah.
But yeah, thank you.
I certainly like to
Thank you.
talk about the gold thing because it's like something that people can identify with, and maybe you think, oh, everyone knows where gold comes from. It's the ground, but actually, yeah, it's now we know it's stars, and we only figured that out two or 3 years ago. So that's
Yeah. Well, it does come from the ground, but
yeah, that's.
but yeah.
So-
Yeah. Well, thank you so much. This was
Sure.
really great.
Great. Well, thanks
I'm
for
sure we'll get good use out of it.
awesome.
So thank you.